So when we are going to try determine the empirical formula, you're either going to be given two options. You'll either be given the mass of each of them or the percentage of each of them. So in this worksheet, we're going to start with number one, be given the mass, and then number two, they give you the percentage, and you have to do a mass. So number one, you're going to start with writing out what they gave you, 0.0134, and then grams, and it's iron that we're talking about. And then it says 0.00769 grams sulfur and 0.0115 grams oxygen. So we've been practicing percentages and ratios because all an empirical formula is the ratio of how much each of these there are in this compound. So in order to find that, we're going to have to get to something that is relatable, like apples to apples with all of them. So currently we've got how much is each of them in this compound, but if we take that and convert it to moles of a substance, we then can actually compare them. And so what we're going to do is we're going to say if we've got 1 mole of iron, what is the mass of iron? If we have 1 mole of sulfur, what is the mass of sulfur? 1 mole of oxygen, what is that mass? So you're just going to look at your periodic tables and find that mass. Guys, I've given away all my periodic tables. Can you give me the mass of iron? 845. And then sulfur? Okay, so now what we're going to do is we're going to take that mass they've given us, the experimental mass, and we're going to divide it by the mass of 1 mole of each of them. And then when you write your answer, you're going to want to make sure that you pull out at least 6 digits, at least 6 significant digits. Remember, you got to write it like an ionic equation. All right, so when we take 0.0134 divided by 55.845, I'm going to write this in scientific notation and pull 6 significant digits. 2.399. It's 49, but I'm going to go 50, and that's times 10 to the negative fourth. And the unit here would actually be moles of iron. If you notice, your mass of iron crossed off for each of them, and you're in moles of iron, which is the SI base unit for amount of a substance, which is how we now can use these numbers that we're getting to figure out the exact ratio that's present. So now next, 0.00769 divided by 32.066. And in scientific notation, I get 2.398. So 1, 2, 3, 4, 1, 8. You want to pull at least 6 digits for this step every time. That way, in theory, it would be best to pull everything on your calculator, but this way you at least get enough that you're going to get an accurate representation of what you should be looking at. Now last is 0.0115 divided by 15.999, and I'm going to get 7.18795 times 10 to the negative fourth. Now the last step is we want to figure out what ratio each of these are, if that's how much there are of each of them. So this is how many moles of sulfur are present, and this is how many moles of oxygen are present. But we want to compare these in an easy to read fashion. So the empirical formula is essentially this ratio put into a whole number. So in order to put it into a whole number, remember when we did like 2 out of 20 as a ratio, if we wanted to simplify that, we would say it's 1 out of 10. But what we're essentially doing mathematically is we're dividing both of them by that smallest number, because I divide this by 2 and divide this by 2, whoops, and then I'm going to get 1/10. Okay, so that's what you're doing when you're simplifying this ratio. We're going to do the same thing here. We're going to find which one of these is the smallest number, and then we're going to divide all of them by that smallest number. So let's start with looking at these numbers. Now, because they're in scientific notation, it makes it a lot easier to look at them. So for instance, this guy right here, my oxygen, I can very quickly see it's definitely not the smallest. It's much, much bigger. They all have the same exponent. So I can just look at this base. So this is 2.3 and then 998. So that makes this guy our smallest number. So now I'm going to divide all of them by the value I got for my sulfur there. All right, so if I divide all of them by the 2.398 times 10 to the negative fourth. Now when you type this in your calculator, you can try it if you want, but if you do it with the exponent and just do it with the base, you're going to get the same thing. Okay, this is going to give you 1 every time. If you divide anything by itself, you're going to get 1. Now if I'm going to divide the next 2, do the same thing, because I want to see how does this relate to that guy. So I'm going to do it here again, and then I'm going to do it down here again. And once I divide all of them out, I'm going to see that this top one is going to be approximately 1. What you see on your calculator is like 0.999 and then a few digits out. If it is within a tenth of a whole number, okay, less than a tenth off, you can round up. So since it's 0.999, I can say that that's about 1. Now when I do the bottom one, I'm going to type on my calculator 7.18795 divided by 2.398. Why did I only pull 4 digits? Oh, I didn't get all of them? Is that what happened? What happened there? Oh, I didn't pull all the digits. Shoot. So 8 and then 1/8. That's what I got. So again, this is the smallest number that I'm using, this one right here. For some reason, I didn't write the last 2 digits there. 1/8, 1/8, 1/8. Okay. So when I do that, I'm going to get about 2.997 and so on. So again, because it's within a tenth of a whole number, I can actually round this to about 3. So right here, I came out to 3 different whole number ratios. Now when I start with this, I would have said that my chemical formula has iron, but I don't know how many, so I'd say X. It has sulfur, but I don't know how many, so I'd say Y. And it has oxygen, but I don't know how many, so I would say Z. Just some basic variables, knowing that I got to find the numbers for those. And when we're writing a chemical formula, we're always going to work left to right in the periodic table. Noticing that sulfur and oxygen are one on top of the other, but oxygen's going to tend to follow other things. Think of like sulfate and sulfite and carbonate and carbonite. All right, so now we know our X, our Y, and our Z because we just found that the simplest ratio means I'm going to have 1 part iron, 1 part sulfur, and 3 parts oxygen. So my empirical formula, which is my simplest form, is going to be FeSO3 for number 1. Remember, if there's only one of them, you do not have to write it. So guys, double check there. Your number 1, you got FeSO3. Okay, so now let's go ahead and do number 2. Now number 2 is slightly different. This is a more typical example of what it would look like. They're usually going to give you a percentage. So that's why in the instructions it says, number 1, change the percent composition to grams. Okay, so what we can actually do, because it is a mass of each of these. So let's say at number 2, we've got 32.8%. I'm just going to write what I have first. That's of chromium, and it's 67.2% chlorine. Now remember, when we say percent, it means per 100. So what you could do to put this into a mass is you could say, well, if I had a 100-gram sample of this CR something, CL something, all right, I don't know how many I have of each of them. If I had 100 grams of it, I would then be able to tell that 32.8% of it would actually give me 32.8 grams of chromium in that 100-gram sample. Your textbook will say unknown sample is usually what they say over the unknown down here. Okay, so we're able to say that this percentage actually can be written just like that. Okay, so then this percentage, the 67.2, we can say grams of chlorine are going to be found in a 100-gram sample of this unknown substance. All right, so I'm going to just erase these guys for now because now we've got what we want. All right, so now we can approach this problem just like we did the last time. And even though there's that 100 gram on the bottom, we can just pretend like it's not there because when you're done, you're just finding a ratio. And if you divided everything by 100, it's just going to make your number smaller and not actually change your results. So I'm going to do the same step we did last time. We're going to figure out, well, if I've got 32.8 grams of chromium, I want to know that realistically, what do I really have? And the easiest way to do that is to get the SI base unit of a substance and figure out how many moles of it I have. So I'm going to look to my periodic table and see what mass chromium has, and then I'm going to look to my periodic table and see what mass chlorine has. Okay, and so then we'll have grams of chlorine here and grams of chromium here. I'm going to give you a second, get those in, do the math. Again, you don't actually have to do this because you're doing it to both and you're only looking for the ratio. It's not going to change your numbers. If you want to do it, you can. It won't hurt. It just makes your number a lot smaller. Well, 2 places smaller. All right, go ahead and try do the math quickly. All right, on the bottom for the chromium, we should have gotten 51.996. grams, and then on the chlorine, we would have gotten 35.453 grams. Now, when we type that into our calculator, again, we got to pull at least 6 digits. So we're going to do 32.8 divided by 51.996, and I am getting 0.6308. So I got 4, I got to pull 2 more, 18, and that's moles of chromium present in this sample. And now this one, I'm going to take 67.2 divided by 35.453, and I'm going to get 1.895. I've got 4 digits, and then 4, 7. Okay, again, round up, 5 are above there, and that's moles of chlorine. Now, just like before with the ratio, we're going to divide by the smallest, and when we divide chromium by itself, it's obviously going to get 1. So here we're going to, I'm just going to highlight the exact same thing, and then we're going to divide by this, and then divide by it again. And when we do that, this one is going to give us about 1. Okay, exactly 1, divided by itself. But if we take the 1.89547 divided by 0.630818, I'm going to get about 3. So that tells me I've got 3 parts chromium to 1, I wrote that, sorry, it's chloride. 3 parts chloride to 1 part chromium. So it's going to be CrCl3 for number 2. All right, now let's go on and try number 3. Go ahead and get your number 3 set up. All right, notice it's saying that that is number 81 in your periodic table, which is thallium, not tellurium. All right, so it's starting with 0.463 grams of TL. Okay, we know we're going to take it times the molar mass. And then 0.0544 grams carbon. Again, molar mass. I'm going to need more room here. And then we've got, so I've just done carbon. Now we've got 0.00685 grams hydrogen. Again, molar mass. And then 0.0725 grams oxygen. And here we go. All right, so the very first one, we know if we have 1 mole of this guy, we just look at the periodic table, 1 mole of carbon, just look at the periodic table, 1 mole of hydrogen, 1 mole of oxygen, now I gotta look at number 81 on my periodic table to find that mass, which we probably know by now, 204.383 grams of tellurium. All right, now when we do this math, so 0.463 divided by 204.383, I'm going to get 0. I'm actually going to put this in scientific notation just to make it easier. So it's 2.26535 times 10, and you have to move it 1, 2, 3 places to the right. Next one, you're going to go 0.0544 divided by 12.011, and you're going to get 0. Oh, scientific notation again. 4.52918 times 10 to the negative third again. And then hydrogen's 0.00685 divided by 1.008. And I'm going to get 6.79563 times 10 to the negative third. At the bottom, 0.0725 divided by 15.999. And you're going to get 4.53153 times 10 to the negative third. All right, now these are telling me the ratio in moles of each of these. So the top is probably going to be our smallest number, and it's in scientific notation. It makes it pretty easy to see. This guy and this guy are very similar. The top number is a bit smaller there, so we're going to go ahead and divide all of them by that. So I'm actually going to type divided by, this guy. Oh, goodness gracious. So I'm going to divide by that, and I'm going to divide them all by the smallest. Divided by that, divided by that, divided by that. And what you'll notice is even if you put in scientific notation and pull all those digits, it's going to be the same as if you didn't, which is good considering I forgot to grab that guy there. Because technically that's what this is. Oh my goodness, I should just write it. All right, so when we divide them all by the smallest, obviously this top one's going to come out to about 1. Now the next one down, we can just take 4.52918. That's times 10 to the negative third, divided by 2.26535. And I'm going to get about 1.999. So again, within a tenth, I can say that's about 2. Now this one is 6.79563 divided by 2.26535. And I'm going to get 2.999 this time, so that's about 3. And then 4.53153 divided by 2.26535. I'm going to get about 2. All right, so what that tells me is TL, but there's 1. Carbon is 2. Hydrogen is 3. Oxygen is 2. So this is my empirical formula for this number 3. All right, I'd like you to go ahead and try number 4 for homework tomorrow. I'm just going to give you a hint. Remember, percent means per 100. So if that is 67.1%, what that means is we can assume 67.1 grams of zinc in a 100-gram sample. And then you would take 100 minus 67.1 to get the other mass. Okay, so then you would have that for your oxygen and do the same process.